Hi, this is S. Lakshmanachari, working as Assistant Professor in the Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. Today, we are going to discuss the logic micro operations. So, already in previous classes, we have seen about what is micro operation and the different types of micro operations. So, micro operations are the operations that are performed on the data stored in registers that are called micro operation. So, these micro operations are different types: register to register transfer micro operation, arithmetic micro operation, logic micro operation, shift micro operation. So in previous class already we have discussed about arithmetic micro operations. Now let's start the logic micro operation. So logic micro operation are the binary micro operations implemented on the bits saved in registers. Okay. So here, these logic micro operations we are performing on the bits stored in the register. So here, these logic micro operations we are implementing bit by bit. Okay. So these operations treat each bit independently and create them binary variables for them. So, for example, if you consider a exclusive OR gate, exclusive OR micro operation. So with the contents of the two registers R1 and R2. So here, so P column R1 exclusive OR operation with R2 to the R1. So this expression it indicates that the contents of R1 register we are performing exclusive OR operation with the contents of the R2 register. So once we have performed this exclusive OR operation, the result automatically will be stored in the R1 register. So that means after performing exclusive OR operation, the result will be transferred to R1 register. So this column, P column. So this is a conditional transfer. So that means P, that means this column it acts as a if statement in programming language. So that means if P is equal to 1. So that means if P is equal to 1, then only it performs exclusive OR operation. So that is the meaning of this expression. So it determines the logic micro operation to be implemented on single bits of the register supported that the control variable P is equal to 1. So if P is equal to 1 only, if the condition met, then only the exclusive OR operation will be performed. So consider that each register has 4 bits. So here we are considering two registers. One is the R1 register and another one is the R2 register. So we are considering 4 bit in length. So that means the length of every register R1 and R2 is 4 bit only. So the content of R1 register will be 1010 and the content of R2 register will be 1100. So see here. So the content of R1 will be 1010 and the content of R2 register 1100. So once you are after performing exclusive OR operation, the result 0110 because we are performing a exclusive OR operation on individual bits. So if you consider this first bits, so what is the exclusive OR of 0 and 0? So that means if the truth table for the exclusive OR is XOR. Okay, suppose if A and B are the inputs, then output. So the input combinations are 0, 0, 0, 1, 1, 0, 1, 1. So these are the input combinations. Okay, because the inputs are 2. So the number of input combinations are 2 power 2. So 4. So 4 possible input combinations are there. So output. So the output for the exclusive OR gate, the output will become 1 if the inputs are different, and the output is 0 if the inputs are having same values. So that is the truth table of the exclusive OR. So according to that, so 0 XOR with 0, so you will get 0. Next, 1 exclusive OR with 0. So inputs are different, so you will get 1. Next, 0 exclusive OR with 1. So inputs are different, so you will get 1. And last bits 1, 1. So inputs are same, so you will get 0. So this is a output for the exclusive OR gate. So when this exclusive OR operation will be performed only if P is equal to 1. So if P is equal to 1, then only the exclusive OR operation will be performed. So coming to the logic micro operations. So total there are 16 logic micro operations are available. So these are all. So it is a representation of all these operations in a Boolean function and also representation in micro operation. Okay, so in micro operation we are specifying using some replacement operator, that is arrow. Okay, and it is a name of the micro operation. So let's start with f naught. So the Boolean function f0, so that is equal to 0. So the same Boolean function in a micro operation we can specify like this: f arrow 0. Okay. So what is the name of that micro operation? That is a clear. So clear means we are loading the 0 to the register. We are loading the 0 to the register F. So F is a register, the name of the register. Okay. So that is the first one is the first micro operation is a clear. And coming to the second one, so that is a F1. In Boolean function, we will represent F1 is equal to x into y. So that dot it represents multiplication operation. So x into y. So x into x dot. So that dot it represents AND operation. AND. Okay. So the same AND operation we can represent in micro operation A cap B. So this is so the name of the operation is AND. So AND operation. So logical AND. So this is a logical AND. And F2 x into y bar. So in Boolean function we will write F2 is equal to x into y bar. X into y bar. So the same Boolean function we can represent in micro operation. So that is F arrow A and B bar. So it doesn't have any name. Okay, it doesn't have any name. So the expression is A and B bar. And coming to the F3, F3 is equal to x. F3 is equal to x. Similarly, A tends to F4. So that means here transfer. What is the name? The name of the micro operation is transfer A. So that means the contents of register A we are transferring to the register F. So that is F3. F4. F4 is equal to x dash into y. X dash into y. Similarly, the same micro operation, the same Boolean function we can write in micro operation A bar and B. So it is also, it doesn't have any name. And next F5. F5 is equal to y. F5 is equal to 5. So in Boolean function the inputs are x and y, and in micro operation the inputs are A and B. Okay. So F5 is equal to y. Here B transferring to F. So that means the contents are transfer B. The name of the micro operation is a transfer B. That means the contents of B register transferring to the register F. Now coming to the F6. F6 is a X XOR Y dash. So in a micro operation, A XOR B. A XOR B. So the name of the micro operation is a exclusive OR. So exclusive OR operation we are performing. Just before we have seen the truth table and its operation. Next F7. So F7 X plus Y. So plus it indicates OR operation. OR. So A or B. So the type of operation is a OR operation. Next X plus Y whole bar. So that indicates that it is a NOR operation. So the same we can represent A or B bar, whole bar is there. It is a NOR operation. And next X XOR Y whole bar. It is a F9. Okay. So it is a F tends to A XOR B whole bar. It represents exclusive NOR operation. So if you complement the if you suppose if OR gate is there, if you complement that, then you will get XNOR. You will get NOR. Suppose if AND is there, it will become, if you complement that, you will get NAND. Okay. So see here. Next F10 Y bar. So the same we can write in B bar. So that means complement B. Next F11. So F11 X plus Y bar. So the same we can write A or B bar. So it doesn't have any name. F12 X bar. X bar means A bar here in micro operation. Okay, so that means it complementing A. Next F13 X dash plus Y. So the same we can write. So X means here A, plus means R, Y means B. Okay, so it doesn't have any name. F14 is equal to X into Y whole bar. So already we have seen. So X dot Y, that means it represents AND operation. So if AND is there, if you use a complement at the output of the AND, then it will become a NAND. So whole bar is there here, X into Y whole bar. So that represents NAND operation. So A and B whole bar. So it represents NAND operation. So the last function that is a F15. So that is equal to 1. So all ones to F. So that means we are transferring all ones to the register F. So set to all ones. Okay. So these are all the different 16 logic micro operations. So let's see their truth tables. So these are the truth table. So already we have seen 15 micro total 16 micro operations we have seen. So this is a X, Y. So X and Y are the inputs, and F0 to F15. So these are all the outputs for different logic micro operations. So let's see. So X and Y are the inputs. So 0, 0, 0, 1, 1, 0, 1, 1. So F0. What is F0? F0 is clear. So clear means we are clearing the register. So that means all are zeros. Coming to the F1 function. What is F1 function? F1 function is a AND operation. So what is AND operation? If both inputs are logic 1, then only the output will be logic 1. Otherwise, the remaining all outputs are zeros. Okay. Coming to the F2. F2 is a x into y bar. X into y bar. So it doesn't have any name. X into y bar. So what is y bar? Y bar means complementing the y. So y 0 is there. So it will become 1. 1, 0. 0 becomes 1. 1 becomes 0. So we are performing AND operation between this x and this y bar. So what you will get? 0 into 1, 0. 0 into 0, 0. 1 into 1, 1. 1 into 0, 0. So that is F2 function. F3. F3. Okay. F3. So what is F3? F3 is equal to x. That means whatever the x values are there, that will be transferred to the register F4. Okay. So in x, what are the values are there? 0, 0, 1, 1. So the same 0, 0, 1, 1. So in the X register, whatever the values are there, the same values will be transferred to the register F4. Okay. Next F4. F4 x bar into y. X bar. X bar into y. So already we have seen x. So here x values are there. So what are the x dash value? X dash are 0 becomes 1, 0 becomes 1, 1 becomes 0, 1 becomes 0. So these are all the x bar. So x bar into y. So already y values are there. So we are performing AND operation. So 1 into 0, 0. Okay. 1 into 1, 1. 0 into 0, 0. 0 into 1, 0. Okay. So that are the F4 function. Coming to F5. What is F5? F5 is equal to y. That means whatever the values are there in the y register, that are transferred to the F5. So 0, 1, 0, 1. So 0, 1, 0, 1. So that is a F5. Next F6. What is F6? X exclusive or y bar. Okay. So that means exclusive OR operation. Exclusive OR operation. We are performing exclusive OR operation between the inputs. So what is the XOR operation of 0, 0? You will get 0. Exclusive OR operation of 0, 1, 1. 1, 0, 1. So that means if different inputs are there, you will get logic 1. If same inputs are there, the outputs are 0. That is F6. F7. F7 x plus y. X plus y. Okay. So x plus y. That means operation is a OR operation. What is OR operation? If any input is logic 1, then output will be logic 1. So here in the first case both are zeros. So 0. In remaining case, in the next case 0, 1. So one input should be 1. Here 1, 1, 1. Because in remaining cases, one of the input should be, one of the input is logic high. So that's why outputs are logic 1 here. Next F8. F8 is x plus y whole bar. So that means here A or B bar, NOR operation, NOR. So what is OR operation? OR operation is the F7. So it is a OR. So if you complement this, then you will get the NOR. So here 0 is there. Complement 1. 1 complement 0. 1 complement 0. 1 complement 0. Okay, that is F8. Next F9. What is F9? X XOR Y whole bar. So that is equal to exclusive NOR. Exclusive NOR. So where is the exclusive OR? The function is F6. It is XOR. If you complement that XOR, then you will get the exclusive NOR operation. So exclusive NOR operation. So that means 0 become 1, 1 become 0, 1 become 0, 1 become 0 become 1. So that is a F9. F10, Y bar. Y bar. That means complementing B. Complementing B. So already here it is there. Y. So this is A or B. So this is B. What is B bar? B bar. So that means 0, 0 is a B bar, 1, 0, 1, 0. So 1, 0, 1, 0. This is B bar. Complement. Next F11. X plus Y bar. X plus Y bar. So A or B bar. It doesn't have any name. What is this? X plus Y bar. Y bar is already here we have written. AND operation. That means we are performing AND operation between X and X Y bar. So that means 0 or 1. 1. 0, 0, 0. 1, 1. 1. 1, 0. 1. Because we are performing OR operation. If any one input is logic high, then output will be logic high only. F12, X bar. X bar. What is X bar? It is X. X bar will be this one. So complementing of X. So 0 is there, 1. 0, 1. 1, 0. 1, 0. So double 1, double 0. So double 1, double 0. Next F13. F13. X bar plus Y. X bar plus Y. So this is a X bar. So this is Y. So we are performing OR operation. So 1, 0. 1. 1, 1. 1. 0, 0. 0. 1, 0, 1. So we are performing this one. Last case 0, 1. 1. Next F14. X and Y whole bar. So that indicates NAND operation. NAND. So which function is performing the AND operation? AND. F1. So this is a AND. So if you complement that, you will get the NAND operation. So 0, 0, 0, 1. So it will become 1, 1, 1, 1, 0. 1, 1, 1, 0. So this is NAND. And the last one F15, that is equal to 1. So that indicates that the register is loaded with all ones. So F15, all ones. The register is loaded with all ones. Okay. So these are the different total 16 logic micro operations. So the same logic micro operations we can implement using some hardware. Okay. So the hardware implementation of logic micro operations require that the logic gates be inserted for each bit or pair of bits in the registers to perform the required logic function. Although there are 16 logic micro operations, most computers use only 4 basic micro operations, that are AND, OR, NOR, complement. So these are the basic operations. So using these basic operations, we can implement further logic micro operations, because so here these are the basic. These 4 are the basic. Suppose if I want NAND, if I want a NAND micro operation, then I can implement this with using these basic operations, because to implement this NAND, what I require? I require AND operation and NOT. So this is AND and this is a complement. Complement is a NOT. So I require these two. I require this and this one, complement. So by combining the two, I will get the NAND operation. So like this, we can implement any logic micro operation using these 4 basic micro operations. So The figure below shows one stage of the circuit that generates four basic logic micro operations. So for that we require four gates and one multiplexer, one 4 by 1 multiplexer. So this is a hardware implementation. So it is a 4 by 1 multiplexer. So that means four inputs are there. Input 0, this is I0, this is input 1, input 2, input 3. So total four inputs are there and one output is there. I is the output. And two selection lines are there. So we can determine the number of selection lines using formula 2 power n. So where n is the number of selection lines. So how many inputs are there? 4. So this we can write 2 power 2. So that is equal to 2 power n. So where n is 2. So that means we require two selection lines, S0 and S1. And to implement all these four basic operations, we require four gates: AND gate, AND, OR, XOR, complement, NOT. And A and B are the inputs. So all these inputs are connecting to the applying to the all the gates, so that according to that you will get the output. So in multiplexer, out of the four inputs, only one of the input will be connected to the output based on the selection inputs. So if the selection lines are 0, 0, if S0 and S1 both are 0, 0, then the AND gate will be connected to the input 0. So this input 0 will be connected to the output. So the AND gate will be connected to the output if S0 and S1 both are equal to 0. So it performs AND operation. So if S1 is equal to 0 and S0 is equal to 1, then it performs OR operation, because when S1 0 and S0 1, then this I1 input will be connected to the output. Similarly, S1 1, S0 0. In this case, the I2 will be connected to the output. Similarly, the last case, when both the selection lines are logic 1, then it performs the complement operation, because the I3 input will be connected to the output. So in this way, we can implement all these four basic operations using 4 by 1 multiplexer. And coming to the applications of logic micro operations. So these logic micro operations we can use for different applications. So let's see one by one. So these logic micro operations, it can be used to change the bit values of a register, or delete a group of bits in a register, or insert a new values into the register. So using these logic micro operations, either we can change the bit values of a register, or we can delete, or we can insert. So the applications are the selective set, selective complement, selective clear, mask, insert, clear. So these are all the different applications of logic micro operations. So let's see one by one. First one is a selective set. Selective set. So the selective set operation, it sets to logic 1 the bits in register A where there are corresponding ones in the register B. So it doesn't affect the bit positions that have zeros in B register. So it can clarify with one example. So A register and B register. So we have two registers, A and B. So A register content before the selective set operation. So A register, it contains 1010, B register it contains 1100. So what is selective set? So using this selective set, we can set to 1. We can set to the 1 the bits in register A. So this is register A. So in register A bits we can make it 1, logic 1, where the corresponding ones in the register B. Okay. So for that, see the B register data. So where ones are there? So this one and this one. So in this positions, logic 1 is there. So the corresponding bits in the register A will make logic high. So if you consider, so this is a D0, D1, D2, D3. So if you consider D2 position, so the corresponding bit in register A is 0. So by using this selective set, we can make that D2 position, we can make it a logic 1. So it will become 1. So it will become 1. Okay. So next, so if you see the last position, that is 1. The corresponding bit in register A is already 1. So no need to change. So already it is 1. So no need to change. If it is not 1, then we can make it logic high. Okay. So after performing selective set, what are the contents of the register A? That is 1, 1, 1, 0. Okay. So that means the D2 position, it is actually 0. But after performing selective set, it becomes logic high. Okay. So that means here, what we are doing, so here, the OR micro operation. So we are using a OR micro operation. OR micro operation can be used to selectively set bits of register. Next one, selective complement. So the selective complement operation complements bits in A, where the corresponding ones in B register. So for that, it can understand with example. So see here, see the B register. So where the ones are there? So this is D0 position, D1, D2. Otherwise, you can name it B0, B1, B2. This is B3. So B2 and B3 positions are logic ones. Okay. So corresponding bits in A register. So that means this is A0, A1, A2, A3. Okay. So we have to where ones are there in B register, corresponding bits in A register has to be complemented. So in A2 0 is there. So that means that will become 1. Similarly, in A3 is logic 1. So that has to be complemented. It will become 0 because ones are there in the B register. Where the ones are there in the B register, that corresponding bits in A register to be complemented. So that's why here. So after performing selective complement, selective. So that means we are not complementing the entire register. Only a selected bits will be complemented. So that's why it is called selective complement. So the exclusive OR. So the exclusive OR micro operation can be used to selectively complement the bits of a register. Okay. So suppose if you perform a exclusive OR operation, what will happen? 0 exclusive OR with 0. So 0. 1 exclusive OR with 0. 1. 0 exclusive OR with 1. 1. 1 exclusive OR with 1. 0. So that means the result is equal to the performing exclusive OR operation between the A and B registers. Next, selective clear. Selective clear. So that means using this selective clear operation, we can clear to 0 bits in A only where there are corresponding ones in B. Okay. So we can clear the A register where the corresponding ones are there in the B register. So you can clarify with example 1010. So this is A0, A1, A2, A3. So this is B0, B1, B2, B3. So where ones are there in B register, B2 and B3. So that corresponding bits has to be clear. The corresponding bits in register A has to be cleared. So see here. If you see B2, what is the corresponding bit in register A? A2. Because A2 is already 0. No need to clear that. So that's why already it is 0. Consider the B3. B3 is logic 1. So corresponding bit in A register is A3. So A3 is 1. So we have to make it 0. So that's why after performing select to clear, the A value, A register value will become 0010. So this is corresponding to logic micro operations A and B bar. Next, mask. So the mask operation is similar to selective clear operation, except the bits of A are cleared only where there are corresponding zeros in B. Okay, so it is similar to the selective clear, except there are corresponding zeros in B. But in selective clear, we are clearing where the corresponding ones in B register. But here we are making, doing it corresponding zeros in B. Okay, so see here, example 0110 111010. In B register 0000 1111 B register. So okay. So here, so we have to see where the zeros are present in the B register. So in B register where the zeros are there, if you named B register, this is B0, B1, B2, B3, B4, B5, B6, B7. So the B4 to B7 positions are 0. So we have to consider this. The corresponding bits in register A, that means A4, A5, A6, A7 has to be masked. So that means masked means we are making that bits to 0, logic 0. So if you consider B4, the corresponding bit in the register A, A4. So that is already 0. So no need to change it. And coming to B5 position, the corresponding bit in A register is A5. But here it is a logic 1 is there. Logic 1. So we have to make it logic 0. So logic 0. Similarly B6. So corresponding bit in register A is the A6. A6 is equal to logic 1. We have to clear it. So it will become 0. B7. So the corresponding bit in register A is A7. So A7 is already 0. No need to change. Already it is 0. So after performing the mask operation, the contents of register A is 0000 1010. So that means upper nibble. Nibble means 4 bits. Upper 4 bits are masked after performing the mask operation. And coming to the insert. The insert operation inserts a new value into a group of bits. So we are inserting a new value into a group of bits. So that's why it is called inserter. And this is done by first masking the bits, then ORing them with the required value. So in order to insert, first we have to perform a masking operation, and then we are performing a OR operation. So already we have seen masking. Okay, masking operation. Okay, so for example, suppose if the A register contains this value and this, so if the A register contains 0, 110, 1010, so we have to mask it. So mask it means we are masking the upper 4 bits. So these are the upper 4 bits. Okay, so that we have to make it 0. So A register before. So 0, 110, 1010. So this is the contents of A register before performing the mask operation. Okay. Next B register. So B register is a 00001111. Okay. So after that, what are the, so after performing masking, then the contents of register A. So that means what we are doing here, we are performing AND operation. We are performing a AND operation. So see here. So 0, 1. If you perform AND operation, 0, 1, 1, 1, 1, 0, 1, 0, 1, 1, 1. So 0 AND with 0, 0, 1 AND with 0, 0, 1 AND with 0, 0, 0 AND with 0, 0. So that means actually the contents of the upper 4 bits of A register should be 0110, but after performing mask operation, that are replaced with zeros. That is a masking. Okay, after masking, we are inserting a new value. Okay, so what is the value we are going to insert? So this is a 1001. So this is the value we are going to insert. Okay, so that's why this value we are performing OR operation with the register A. Okay, so this is A before performing the insert operation. So what value we are inserting? 1001 value we are inserting. So we are performing the OR operation. So 0 OR with OR, 0 OR with 0, 0, 1 OR with 0, 1, 0, 1, 1, 0, 0, 1. So what are the contents of the register A after performing the insert? So 1001, 1010. So we have inserted. Actually, the register content, A register content will be 0110, 1010. That is the actual content present in the register A. But after performing insert operation, the content of A register will be 1001, 1010. So that means here the upper 4 bits are replaced with a new value. We have inserted a new value. This is before, this is after. So we have inserted a new value into the register A. So this is about the insert. Coming to the last application, that is a clear. So the clear operation, it compares the votes in register A and B and produces an all zeros result if the two numbers are equal. So see here. So this is a register A and this is a register B. Okay. So we are comparing these two and we are comparing exclusive OR operation. That means if they are having the same value, then it gives a 0 result. So 0, 0. Same. If same inputs are there, then output is 0. So that means we have cleared the register. So before performing clear operation, what are the contents of the register A? 1010. But after performing clear operation, the contents of register A is 0000. So that means we have performed a clear operation. Okay. So in this lecture, we have discussed about different logic micro operations. So total we have seen 16 logic micro operations on their truth table, and also we have discussed about the applications of this logic micro operations. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.